good morning to NZZQs. I'm Lai Man Ching. Today I would like to explain the introductions in this project. Microwave filter is a linear two-port network. It is used to control the frequency response at a certain point in the microwave system. The aim of this filter design is to approximate the ideal specifications within a reasonable tolerance with real component circuits. This is the common use block diagram for the filter system. Radio frequency signal consists of the desired signal and the unwanted signal. The unwanted signal is like the noise, so that's why the filter is important to filter out the unwanted signals and only pass through the needed signal. This is the four general types of microwave filter, which is low pass filter, high pass, band pass, and also band stop filter. In each general types of filter, it consists of active filters and also passive filter. For the active form, the signal power of the passband region can be amplified, and for the passive filter, it does not amplify the power of the passband. So, what is the insertion loss? Insertion loss is the loss of signal when traveling in and out of a circuit or traveling in and out of a component. When your signal reaches a part of 100%, a loss is registered. This is defined the loss of insertions and is calculated in the decibel units.
My name is Michael. Today I'm going to explain about the theory briefly and also some of the results that we get from the project. First, for lump element filter design, we are using the pi network design due to it is an odd filter. Second, the number of order can be determined by using the graph of attenuation versus the normalized frequency. And the element values we get is from this table, the 0.5 dB ripple table, refer to this line. And the calculation formulas is given by CK and LK by substituting the G value to it. And the bandpass conversion is convert the low pass prototype for shunt capacitor is using this formula, and for series inductor is using another formula down here. For the distributed element filter, there are two major steps, which is the Richards transformation and also the Kuroda identity. The result that we get for the lump element schematic looks like this, with all these values that we obtain from the calculation applied here. And this is the frequency response that we get from the lump element design, and the cutoff frequency is at 3.5 GHz, and at 10.5 GHz there are more than 50 dB of attenuation. After that, the distributed element design have to be used the Richards transformation to get the value of 1 over G here, and then we apply the Kuroda identities, which is the conversion from shunt stop to series stop for both sides of this. And finally, we get the series stop diagram here, and then now we are going to convert this series stop to the open circuit shunt stop, which will be finally looks like this, and this is the normalized impedance open circuit shunt stop diagram. And then we will going to denormalize it by applying 50 ohm impedance for all these values. And this is the schematic diagram looks like in ADS. This is the untuned one, and the width and length can be determined by using the line count function in ADS. And for the normal transmission line, not the 50 ohm one, the other one of this transmission line will have a 45 degree of electrical length, whereas the 50 ohm one have 90 degree of electrical length. This is the first frequency response that we get before the tuning done. And we can see the cutoff frequency value and also the attenuation value at frequency of 10.5 gigahertz is far away from the expected result. So we tune the elements, not the 50 ohm one and not the width of it. We just tune the length of some of these other transmission line, and then finally we get a frequency response graph that fulfill the expected result, which is at 3.5 gigahertz is the cutoff frequency started, which can be proven by the blue line, which is the reflection of the frequency response. At the point M2, the frequency 10.5 gigahertz will have a 50 dB of attenuation. And next, we apply this tune schematic design to generate a layout for the low pass design. So this will be the layout looks like, and the length is different due to the tuning has been done to this schematic. That's all from me. Thank you.
This is the part of manual calculation. With the given specification, center frequency is used to find the lower cutoff frequency and also the upper cutoff frequency. After that, the frequency multiplied with 2 pi to get the angular frequency. Then substitute into this formula to find out the delta. With the n equal to 5 in 3 dB ripples, the G value can be found out with using n equal to 5. N equal to 5. Next, this is the formula for the series LC circuits and also the shunt LC circuits. For the series LC circuits and also the shunt LC circuits, sub in the G value, the delta values and also the angular frequency value in order to get the values of inductors and capacitor. Before design the bandpass filter, low-pass prototype is needed. This is the T combinations network of low-pass filter. Then I will convert it to the bandpass filter. So this is the bandpass filter schematic diagram. After that, I will apply the circuits in this ADS system. Then I will substitute the values of inductors and capacitor that I get from the manual calculations. Then I will stimulate it to get the frequency response graph of the bandpass filter. So this is the label of lower cutoff frequency, center frequency, and also the upper cutoff frequency. The dB of the lower cutoff frequency, center cutoff frequency, and also the upper cutoff frequency can get from this label. That's all from me. Thank you.